Hello, welcome to Chemistry Buds. Today I will discuss the phase diagram of a system with a congruent melting point. In the last video, I have discussed elaborately how the compound formed with a congruent melting point. So now we are continued discussion of the two component condensed system. So it is important to describe in a good manner in the examination. So this is very important. So understanding is a different thing and reproduction in the exam paper is different. So from exam point of view, the today's video will be very important. We have to represent and explain correctly the phase diagram. So in this system, we have taken the composition in the x-axis, composition, okay, and the temperature in y-axis, okay. So in the extreme left is A is 100% and B is 0%, and extreme right the A becomes 100% and the A is 0% and B is equal to 100%. Okay. B is 100%. So we mark the different points. So for pure A, the melting point is this is A, and for pure B, 100% B, the melting point of B is B, and we have the U-Tate, say it is C, and the point, this is the congruent melting point as I have explained yesterday. So this is D and this point is E, and we have two more points. So this is X and this is Y. Now in this phase diagram, what we have to do, that is we have to explain the different points, the curves and the area bounded by the different curves, the regions, and also we will calculate the degree of freedom for the points, curves and the region. So as we have taken, so this graph and the experiment we have to consider together. So we have taken a mixture of A plus B, okay, and when A plus B is heated to a very high temperature, if it is pure A, then this will melt at this point, and when the melt will be condensed, the solidification of A will start also at this point. So the melting point and the freezing point are same for the substance, and this is a point. So this point is the freezing point of A, P of A, and this is the cooling curve or freezing point curve. So in this line we are getting the solidification of A at a different composition. Okay, so A solid is formed. So when A solid is formed, we are taking the mixture and heat it. It is soluble in the liquid phase, and when we cool it, the solid solidification of A will start here, and more solidification will start here as we move along this curve. Okay. So any point on this curve is in equilibrium. This represents the equilibrium between solid A and the solution. Okay. So this curve is a AC, your freezing point curve. Okay. So this is the solution. Okay. So if you take the area bounded by this curve, say ACX, so this is in this region, so you will find the solid A solid plus solution. Okay. So and this point is your utility where you are getting two solids, that is a solid A and AB. Okay. So this point is a triple point, and this is utility, and this is also the invariant. And if we see in this region, okay, so in this region the substance present, that is solid A and solid AB. Okay, so two solids present in this region, and this is the CD curve and DE curve. Okay, so this is, and these two curves are called the solubility curve of AB, because the new compound is formed at this composition and this temperature. So this is the eutectic temperature and first eutectic composition of A and AB. So this is also the solubility curve. Again, if you have taken this the point B, this one, this is the freezing point of pure B. Okay, and in this region you will get a solidification of differential solidification of B. So any point on this curve, this is in equilibrium with the solution of A. Okay, solution of A. And the point E, this is also the eutectic point where the solid AB is formed and the solid B is formed. Okay, so two solids are formed, and if you mark the region, say in this region, so in this region you will get two solids, that is AB and B. So and in this region you are getting solid A and solid AB. So in this is the region where you will get AB. Okay, so in this region you will get a solid AB solid. Okay. So we have described this where is the what. So this is also this curve is called the freezing point curve, FP curve of B in presence of A, and this is the freezing point curve of A in presence of B. Okay, so in the solution there is A and B, not AB. Okay, so when this point, this is the congruent melting point. Okay, so this point B, it is a congruent melting point. Okay, so we have to explain the different points, the different curves and the region. And if you consider the area above the curve, A, C, D, E, B, area above this, so this region, okay, in this region, so this is the solution of AB, one phase. Okay, so this is the congruent melting point, and this composition is a congruent composition. So this point is also invariant. Now we will calculate different degree of freedom for different points on the curves. Okay. So let us see that we have the degree of freedom formula, that is F is equal to 3 minus P. Okay. So if we are considering this region, okay, the area above the if we consider the area above A, C, D, E, B. So area above this right mark region, so this area, then only one phase, that is solution of A and B. So the degree of freedom will be 2. F is equal to 3 minus 1, that is 2. So if you consider a point on this curve, so this curve represents the equilibrium of the solid A and the solution. So two phases are there, and the degree of freedom is equal to 3 minus 2, that is 1. So this is a monovariant. Okay, this curve is a monovariant. Okay, so at this point, any point in this region, okay, this is a bivariant. At the degree of freedom is 2, and this region also represents the solid A in solution, because when the solid A is formed, if you consider the experimental setup, the solid A is formed here and it is inside the solution. Okay, so there are two phases. So any point here that is two phase, and it is also monovariant. So any point if you take a point on the curve, that is a monovariant, and in this region also, so in this region, this is in the solution we have AB, the solution, and the solid form is AB here. Okay, so the AB and solution coexist in the container. So there are two phases. So for any region, you can take the degree of freedom is here 1. Okay, and so this is also you take where three phases coexist, and this is a you take, there are two you take the points C and E. Okay, so the C and E are you take the points, and the geometric points are invariant. Okay, so why invariant? Because the three phases coexist, two solids and the solution, the two solids present in the solution of AP. So 3 minus 3 is equal to 0. So for this point, F is equal to 3 minus 3 is equal to 0. So this is invariant, and this E is also invariant. And the point D is the congruent melting point. So in the congruent melting point, it behaves as a single component, because without all the solution will solidify at this temperature, okay, corresponding to this temperature as AB, without changing in composition. Okay, so this is the this point. At this point, it is considered as a one component condensed system. So for general, we have a degree of freedom F is equal to 2 plus C minus P. So for condensed one component, this is the 1 plus C minus P. Okay. So at this point there are two phases and component is 1, so 2 minus 2 is equal to 0. So this is also invariant, invariant point. Okay. So we have calculated the degree of freedom for different curves, different regions, and different points. We have one congruent point, two eutectic point, and two freezing point. That is for pure A and pure B. So there are altogether 5 points, and in this region we are getting the solid A and AB, and in this region, okay, we are getting solid AB and B. So there are 2 phases. When 2 phases are there, it is also monovariant, because 3 minus 2, okay, 3 minus 2, that is 1. So it is a monovariant. So this region is also a monovariant, and so we will sum up that the points, 3 points, to eutectic and congruent, these are invariant. And at this point, freezing point, so this is the one phase, okay. So this is the freezing point. So this is the 2 phases are there. So this is also monovariant. So any point we will take at random, that is a monovariant, and only the solution phase is the bivariant, and the points eutectic to eutectic point and congruent point, melting point, these are invariant. So we have calculated degree of freedom for this, and I hope you can perform any question. It may be objective or descriptive. In the examination, you can calculate degree of freedom and identify the different curves. One more point. So this is this line. We can say this is x1, y1. Okay. So corresponding to a particular temperature, we have 2 different solubility of AB. Okay, 2 different solubility of AB. The compound AB formed, this is one solubility and this is one solubility. Okay, and the compound AB possesses congruent melting point. So this is called retroflex solubility. When this particular compound have 2 different solubility at the same temperature, we say that retroflex solubility. So this is a new concept we should remember for the exam. And with this, I have to conclude this, and in my next video we will see that the ferric chloride system, how the particular system exhibits congruent melting point. Okay. So I hope you are enjoying this video, and don't forget to share among your friends and give your like and comments. So this will be your contribution to my encouragement. Thank you for watching.